In the last video, we looked at a vector v, and it was the vector 4, -3. So if we sketch it in standard position, it looks like this, out to 4 and down to -3. It was about like this, and we said that this was the vector v. So v is equal to 4, -3. So we started with that vector, and what we said was that we could also express v as a linear combination of the standard basis vectors I and j. So we said v was equal to 4i minus 3j, and that this was the same vector v as this vector v here, 4, -3. Remember here that I and j are just vectors. They are unit vectors, they have length 1, and they are the standard basis vectors. But we can write them this way. So instead of writing the vector v this way, we'll say the vector v is also equal to 4 times the standard basis vector I, which we can write as 1, 0, and then minus 3 times j, which is the standard basis vector 0, 1. When we write it this way, what we see is that v is just a combination. It's the sum or difference of a set of scaled vectors. So I have the vector 1, 0. I'm scaling it by a scalar of 4. And then I have the vector 0, 1, and I'm scaling it by -3. And I'm adding those two together. Adding because we're saying we're scaling by -3. So we would say plus -3 times the vector 0, 1. But I basically have a sum, a combination of a set of scaled vectors. And that's really what we mean when we say linear combination. A linear combination is just the sum of any number of scaled vectors. And some of those vectors might be scaled by 1. They don't necessarily have to have a coefficient other than 1. But basically, we're adding up a bunch of vectors, and we might scale them by some constant scalar here. And that is a linear combination. So given our example down here, where we said that v was equal to 4 times the vector I minus 3 times the vector j, that's a linear combination because we're scaling I and j by these constant scalars, 4 and -3, and we're adding those together. Another example of a linear combination could be 2 times the vector a plus 4 times the vector b minus the vector c. I have 3 vectors, a, b, and c. I am scaling vector a by 2, I'm scaling vector b by 4, and I'm scaling vector c by -1, and I'm adding them together to get a sum. And this is just one single vector here, which is a linear combination of the vectors a, b, and c. With that in mind, let's talk about span. And you really just want to think about the span as all of the linear combinations. So here's an example of the idea of span. Remember that the entire xy coordinate plane is R2 coordinate space, or two-dimensional coordinate space. What we know is that R2 is spanned, or it's equal to the span of the standard basis vectors I and j. Let's go ahead and hat those. In other words, if we take the span of I and j, we will get all of R2. What that means is that we can find any vector, or we can write any vector in R2, no matter which vector we pick, as a linear combination of I and j. In other words, if I collect together all of the possible linear combinations of the vectors I and j, that set of linear combinations is just going to be all of R2 space. And we can kind of see why that would make sense. Let's say I have the vector a, and that's equal to 7, -2. And I have the vector b, and that's equal to -2, 9. And let's say I also have the vector c, and that is equal to 0, 4. These are all vectors in R2, and I can express each one of them as some linear combination of I and j. We know that this is equal to 7i minus 2j. We know that this is equal to -2i plus 9j. And we know that this is equal to 0i, so we just won't write that, plus 4j, so we'll just write 4j. No matter which vector I give you in R2, it could be the vector 99, negative 17. It doesn't matter which vector we pick in R2, I can represent that as a linear combination of I and j. And so because I can use I and j to create a linear combination that will represent every single vector in R2, that tells me that the vectors I and j span R2. They cover everything in R2. I can use them to represent everything in R2. So that's the idea of span, because span is all the linear combinations of. So this says that R2 is equal to all the linear combinations of I and j. In the same way, I know that R3 is spanned by the standard basis vectors I, j, and k. And that's because, like we looked at in the last video, no matter which vector I pick in R3, I can use a linear combination of I, j, and k to represent that vector. For instance, if I pick the vector, we'll say the vector d, and in R3 it is 0, 17, negative 4, I can represent that using a linear combination of I, j, and k as 0i, so we won't write that, plus 17j, so 17j, minus 4k. So I have a linear combination here of I, j, and k that gets me to this vector in R3. And there's no vector I can find in R3 that I cannot get to using a linear combination of I, j, and k, or that I can't represent using a linear combination of I, j, and k. So the span of I, j, and k, all the linear combinations of I, j, and k, will represent R3, or three-dimensional coordinate space. Okay, so we know that the span of I and j is going to represent all of R2, and we know that the span of I, j, and k is going to represent all of R3. But are there any other combinations of vectors that will span R2 or span R3? And the answer is yes. We don't just have to use the standard basis vectors. In fact, any two-dimensional linearly independent vectors will span R2, and any three-dimensional linearly independent vectors will span R3. So for R2, in order to get a vector set that spans R2, I need two of them. I need two vectors. They need to be linearly independent, and they need to be two-dimensional. In other words, they need to lie in R2. In order to span R3, I need three vectors. I need them to be linearly independent, and I need them to lie in R3. I need them to be part of R3 space, or three-dimensional space. So for both of these definitions, we can understand here that we need two vectors and three vectors. We can understand that we need them to be in R2 or in R3. The only thing we really don't know about yet is this linear independence idea. And in the next couple lessons, we're going to talk a lot more about linear independence in both 2 dimensions and linear independence in 3 dimensions. But for now, the general idea is that in R2, if the two vectors are linearly independent, they can't lie along the same line. And this should make sense to us because let's say that in 2-dimensional space here in R2, I have this vector that we started with for -3. But then let's say as well that I have this vector right here. I don't even know what the vector is, but it looks like this. So it lies along V. It points in exactly the same direction, it's just a different length. If I take scaled versions of this yellow vector, I'm only ever going to get another vector that lies somewhere along this line. And it might lie over here, it might lie in this direction as well, but it's going to lie somewhere along this line, because if I multiply it by some positive scalar, it's just going to move out in this direction toward V. If I multiply it by a negative scalar, it's going to flip its direction around and move out in this other direction, in the opposite direction of V. But no matter what scalar I multiply it by, it's still going to lie somewhere along this line. And the same is true for V. V is always going to lie along this line, no matter which scalar I multiply it by. If I multiply it by a positive scalar, it's going to continue to head out in this V direction. If I multiply it by a negative scalar, it's going to flip around in the opposite direction and head out up here into the second quadrant. But either way, both the yellow vector and the blue vector, they're always going to lie along the same line here. And so if I want to get to, let's say this point here, 3, 0, there's no combination of yellow and blue vectors that I can take to get to that purple point. I can't add 2 of the blue vector to 1 of the yellow vector and end up at this purple point. And the reason is because these yellow and blue vectors here are linearly dependent. In the case of R2 in the R2 plane, they're collinear. They lie along the same line, or they're parallel to each other. And when you have 2 vectors that are parallel, they are not linearly independent, and they won't span R2. But any 2 other vectors, if I instead took the blue vector and this vector here, and it doesn't matter which vector I pick as long as it's not parallel to, as long as it's not collinear with the blue vector, if I choose literally any other vector, then those vectors are going to be linearly independent. In the same way, instead of lying along the same line, if in R3 my vectors all lie in the same plane, so if I have something that looks like this in 3-dimensional space, so let's just draw some quick 3-dimensional axes like this. So if I have 3-dimensional axes, and then let's say I have a plane that looks something like this, and I connect those here. So I have this plane. If all 3 of my vectors lie in this plane, in other words, if they are coplanar, in R2 we said they had to be collinear. In R3 they have to be coplanar, meaning they lie in the same plane. If they lie in the same plane, and then I want to get to some other point up here, some purple point right here, I'm not going to be able to use any linear combination of 3 vectors that lie in the plane to bust out of this plane and get up to this purple point right here. There's no way for me to get to it, and that's because the 3 blue vectors are not linearly independent. But as long as I have one vector of my 3, any vector, that sticks out of the plane, that is not coplanar with the other 2, but pops out of the plane, if I have this one red vector and 2 blue vectors, in other words, 3 vectors pointing in different directions that are not coplanar, they'll be linearly independent, and I'll be able to use them, a linear combination of them, to get to this purple point, to get to any point in R3. So that's just the basic idea. We'll talk about linear independence in much more detail, but the idea is that your vectors need to point in different directions. They need to be different enough from each other in order for your set of vectors to span R2 or span R3 or span some other subspace, which we'll also talk about later. If your vectors are too similar, for example, if they're collinear in R2 or if they're coplanar in R3, they won't be linearly independent. You won't be able to reach any point in the space, and therefore that vector set wouldn't span the space R2 or R3.